be on standard T2. This theorem that we're going to take a look at today is not an existence theorem. This one actually is very helpful in certain situations and allows us to cut down tremendously on the work needed to solve particular problems that we're going to look at, what kind of problems those are. Let's start by taking a look at the types of problems affected by this theorem. We're jumping back to the side of integration here because we'll be looking at finding how quickly or slowly the accumulation of value happens, or how quickly slowly the area changes. If you look at the following three graphs and envision a paintbrush, so I wish I had a paintbrush here, but let's pretend that I'm just going to make a little paintbrush here. There we go. Let me make a little paintbrush. All right. Here's my little paintbrush. Okay. So you're going to be looking at sorry, there was an announcement. So if you look at or envision a paintbrush, so you have this area underneath the curve. You're starting at 1, and I'm not quite sure how much area I want, but if I wanted to look at how fast the area is changing, if you envision a paintbrush up here where the area is large, you'd have a pretty wide paintbrush that would be able to paint that area as you move left to right. But as you get close to the edge of that, your paintbrush has to become very teeny tiny. So, little tiny paintbrush. And so you'll be painting, but then you're not covering as much area because the paintbrush isn't as big. So if you envision a wall, and if you have a huge wall, I don't know if you've ever seen those, I don't know what you call them, but like people that paint for a living, have these huge like 18-inch rollers, and then they just can cover like a bunch of area in a short amount of time. Well, if you tried to paint a huge wall with one of those, it wouldn't take you very long because the rate that you're covering the area is pretty fast because your paintbrush is pretty big. If you were trying to use a tiny little baby paintbrush, like one that you would use for very detailed work in art class to cover or to paint that area of that huge wall, it would take you a long time to cover that wall. And that's because the width of your paintbrush isn't very big. So, all that to say, if you envision the width or the height between the x-axis and your function as being the width of your paintbrush, here it's very large, or the area that you're covering is very large, so the rate of area increasing is pretty quick. But as you get down to little tiny parts like this, you're not covering as much area, so area is increasing slowly because it doesn't have as much coverage at one time. And you can actually get negative area when it drops below the x-axis. Okay, so area is increasing very quickly in some cases because your paintbrush is large, so you're covering more area as you move left to right. And in some cases, the area is increasing slowly, and that's because there's not as much area covered there. For these types of problems, you are often not given a value for how fast area is changing, or you're not often finding a value of how fast area is changing. Instead, you'll be finding a function that represents how fast the area will be changing at any particular x value. So since we're still dealing with area underneath the curve, we're still going to be looking at integration. But since we're looking at rate of change, how fast that area is changing, we're also kind of going to be looking at derivative. So let's look at a connection here. Let's say you had this situation going on. So my function is sine, and I'm going to use sine of t here. If I wanted to evaluate the area underneath the curve, I'd have to integrate that function from 1, since that's where I'm starting, 2x. I'm not sure where that x is going to end up. We have 3 different x's here. So I'm going to use x to represent, okay, whatever my integration is here. It's going to be a function. I'm not going to get a value, but that function will represent the area covered at any given point. So integrating this, integration of sine is negative cosine. And then if I have limits of integration like this, I'm going to evaluate from 1 to, 1 to x. And then normally we would take f of b, so I'm going to plug in x, minus f of a. So, yeah. Okay, so this would be the function that gives area at any x. Okay, so instead of stopping at x, we're just kind of continuing on until whenever. This is helpful because then if I know I'm supposed to go from 1 to 3, and then I'm supposed to go from 1 to 5, and then I'm supposed to go from 1 to 10, instead of doing this 3 times, once I get a function, I can just plug in 1, 3, 10, or whatever, and get 3 different values very quickly. Now, since I'm looking, or I'm asking how fast the area is changing, this is how the area changes. This function gives the area. And if I'm looking for how fast, that's a derivative question. So now I'm going to take the derivative of that. And if I take the derivative of that, the derivative of negative cosine is sine. Is sine, because derivative of cosine is negative sine. So the negatives would cancel. So you get sine of x. And then the derivative of that value is, hold on. Sorry, somebody came to my door. Is 0 because that's just going to be a constant. So we get the function sine x. So this represents the rate of change of area increasing. Okay, so I hope you followed that logic there. You integrate to find area. This function represents the area at any x. If I want to find the rate of change of how fast area is increasing, then I take the derivative, because derivative is rate of change, and I get sine of x. Notice that this is the same function as what was in my integrand, and that x was the bigger, or the top limit of integration. What the second fundamental theorem of calculus does for us is it helps us skip this middle step, because this pattern will happen every time, or the pattern described in the second fundamental theorem of calculus, where when you have to find the rate of change of area, or of an integrand, instead of integrating and then taking the derivative, since this is already the derivative of whatever you have of your function, we use that fact and we kind of skip over this step. And it's going to look like you're taking your upper limit and just plugging it in, which is what happened here. So go ahead and put, and we'll write out the second middle. We'll write it out, and then hopefully that'll make more sense when we do some examples. Okay, so if your function that you're looking at is the integral from a to some x, and I'm going to make it a u here, function of x. A lot of times your integrand will be written in terms of t, just so that you're using a different variable, where a is a constant. Then g prime of x is going to equal f of u, not fu, f of u times du. So it's going to look like you're plugging in your upper limit into your function and then multiplying by the derivative of whatever that upper limit is. Okay, so again, to qualify, this is the rate of change of area or accumulation of value. So I could ask you a question like, find how quickly the value is accumulating from 1 to x squared. And those are my limits of integration. You would use the second fundamental theorem of calculus. And again, this is not an existence theorem. This actually tells us how to apply this situation. So we're going to find f prime of x. If f of x goes from 2 to 5x, secant t dt. Now, there's no integral. Like, let's just talk through what this would look like if we did it the long way. If we did it the long way, we'd have to integrate this by hand, which actually there's no straight integral rule for secant t anyway. And then when we did actually integrate it, we'd have to take the derivative because my goal is to find the rate of change of this accumulation of value. So a couple things here. This represents area or accumulation of value. And then my upper limit is a function of x in here. So to apply my second fundamental theorem of calculus, g prime would be the same thing as f prime here. F prime of x is going to equal f of u. So your function f is the one that's in the integrand. So it'll be secant of u, which is your upper limit, so secant of 5x, times du, so the derivative of that upper limit function, so times 5. And so your rate of change of area is 5 secant of 5x. So this is a function that gives rate of change of area / accumulation of value. Notice as long as the lower limit is a constant, you can ignore it because when you integrate, that 2 gets plugged in, giving you a number value, not a function. And then when you take the derivative of that, the derivative of a number is 0. So it would not be there in your final answer here. Okay, example 2. An f prime of x. If f of x is the integral from 0 to cosine of 3x squared of square root of t dt. Okay, so I don't want you to integrate this by hand and then take the derivative. I want us to use this shortcut, this theorem, to shortcut that step and get to the result of what it would be if we did it the long way. So f prime of x is going to be f of u, which this is my function, this is my u, so that whole thing is going to go in for t, times du, so the derivative of my upper limit. So we have negative sine of 3x squared times 6x. And then we're going to go ahead and simplify that. So negative 6x sine of 3x squared times the square root of cosine 3x squared. And you're done. So that's all there is to this. There's not much work to show. You just have to recognize, hey, they're asking me for the rate of change of area, so I can shortcut and find f of u times du and go from there. Okay, we'll look at this again tomorrow.